cart M1 with mass 1 equals 0.6 kilograms moving to the right, positive x direction, on a frictionless linear air track, so the wheels don't really matter if it's frictionless. At an initial speed of 1.2 meters per second undergoes an elastic collision, that's important, with a cart with mass 2 equals 0.25 kilograms, initially moving to the left with speed 1.8 meters per second. What is the velocity, the center of mass, the x component of the velocity of the center of mass of the two cart system? Okay, so for this first part, there's two things you have to think about with collisions. One is momentum, two is kinetic energy. And since this is an elastic collision, we know that kinetic energy is going to be conserved. The mnemonic that I use is, when I write kinetic energy, I write energy kinetic, and this E here implies that the energy kinetic is conserved. I know it's a silly mnemonic, but often the silliest mnemonics are the ones that work the best. This is opposed to inelastic collision, where kinetic energy is not conserved. Now, in pretty much all real-life situations, collisions are neither elastic nor inelastic. They're somewhere in between. I guess inelastic is somewhere in between, but that's okay. The point here is, often you'll have collisions, but you can't be like, all right, they start as two objects and then go off as one object, which is what you'd see with a perfectly inelastic collision, and they're not going to come together and bounce with zero deformation, zero sound, and perfectly conserved kinetic energy. So it's not going to happen. This is mostly a thought experiment, but there's a lot of situations in life where we can kind of approximate it. But for this first problem, we really don't need the idea that we have an elastic collision. So for this one, I'm going to say, well, momentum is always conserved. I guess that's pretty much true for everything in life. So we can say that P1 plus P2 initial equals, we could say P1 final plus P2 final, but we could also write this in terms of P, I'm going to call this center of mass final. And since there's only one term here, you could say it's also momentum of the center of mass initial. So basically the momentum of the center of mass is going to be constant here. So we can draw some center of mass point. We'll say it right here, moving, I don't know, which one looks bigger? Mass 1 is probably going to dominate, moving in this direction. And even after they collide, that center of mass will still be moving in that direction. So what we're going to do then is, well, another kind of way of seeing this is the center of mass doesn't have to be inside one of the objects. So in this case, the center of mass will be probably in the middle somewhere outside of both objects. One way to kind of see this intuitively is you have one ball like this, two ball like this, exactly the same. They head towards each other at exactly the same. It would seem reasonable that they hit in the middle, clink, and then bounce off maybe at the same speed going the opposite direction. And it would feel reasonable that the center of mass would be in the middle, and it would stay in the middle, and it wouldn't be moving because it's symmetrical on both sides. There's no way you could justify that the center of mass would be moving to the left or the right because these are both kind of a mirror image of each other. They're both the same. And so when you can't justify it on one side or the other, it feels intuitively correct that it'd be in the middle and it would just stay there. Okay, that's just kind of a warm fuzzies feeling for this problem. So this is the concept we're going to work with up here. And if I was doing this on my own for timed evolution, I would probably write this, and then I would probably write this, and then I'd leave off the initial because the center of mass momentum is timeless. It's the same forever, at all points in time, which I guess is forever. Is that forever? Does forever mean at infinity, or does it mean continuous? Far deeper than I wanted to go in life, let alone this video. Okay, so mass center of mass times velocity center of mass. Okay, so now we got our values. What is VCM? We're going to say that velocity center mass is this guy. Mass center mass, I'm going to say that's M1 plus M2. M2, I'm going to say that's M2, M1, I'm going to say it's M1, and we got our velocities here. Now, these are vectors. So we have to be careful of that and make sure that, because V1 and V2 are in opposite directions, so they have to have opposite signs. So make sure you don't add them together on accident. Well, I guess we are adding it, but we're adding a positive and a negative. So make sure that we don't get a velocity that's bigger than either of them. Okay, focus. We have 0.6, that's mass 1, times 1.2. And I'm going to put a plus here. And then I'm going to do 0.25, and then I'm going to do a minus 1.8. And that will equal, I'm going to divide then by mass, center of mass, which will be 0.6 plus 0.25. And this will give us our velocity of the center of mass. And I say velocity because I'm going to include the direction here. And it's just one-dimensional, so it'll be positive or negative. Turn on our calculator, clear. I'll do 0.6 times 1.2 plus 0.25, which I guess I can divide by 4, times negative 1.8, and I get an answer, 0.27. We'll divide by quantity. I'm going to call this, 0.6 plus 0.25. I was thinking about doing the adding in my head, but that's just asking for trouble. And we get 3176. 3176. Where was that? 0.3176. Okay, I guess there's a 0 there, and in meters per second. And since they're moving in opposite directions, it kind of feels like this should be slower than either of them. So this is going 1.2, this is going 1.8. So yeah, 0.3176 seems reasonable. It's even a possible answer, which is C. So that seems reasonable enough. So to kind of backtrack on what we did there, momentum is conserved, always. Elastic collision, inelastic collision, conservation of momentum. It's a big life thing. And I guess energy is conserved as well, but it's less intuitive. And when you're talking about collisions, heat, sound, all these other things, kinetic energy is not always conserved. But energy as a whole is, so is momentum. So the way we did this was we had momentum 1 and momentum 2 equals momentum of the combined system. I labeled it center of mass. Okay. Whoop. Clear, because we got all we want from that. What is the velocity, Vf, of 1? So after they come together and go apart, what is the velocity of cart number 1? Now this one it's possible though tricky. This is going to be a standard question you'll see a lot. And we are going to use the idea of elastic collision here. So we have two equations we can write up here. We can say momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. And these will be along the lines of mass times velocity. We also have another equation because we know we have an elastic collision. So we have energy kinetic 1 initial plus energy kinetic 2 initial equals energy kinetic 1 final plus energy kinetic 2 final. And these will be of the form 1/2 mv squared. So this, 1/2 mv 2 initial squared. So the deal here then is we have masses, we have velocities, and we can substitute these in for the one for the other. So we know the initial values here. All we don't know is V1 final, which we'll have over here, and V2 final. So we have two equations, two unknowns. This is possible to solve. Though, just because it's possible doesn't necessarily mean it's easy. So I'm not usually a big proponent of memorizing things, of just sticking in your head and having zero conceptual understanding of where it came from, well, without knowing where it came from. But this is a good case where you could solve this, but you're better off just memorizing a formula. And so when you see this sort of situation, with an elastic collision, you're like, okay, elastic collision, final velocity formulas, this is what they are. So you do some substitution, you solve those, and you're going to get something along the lines of mass 1 equals mass 1 minus, not mass 1. See, that's the danger of V1 final equals mass 1 minus mass 2 over mass 1 plus mass 2, the combined masses, times velocity initial 1 plus 2 times mass 2 all over mass 1 plus mass 2 times V2 initial. You might be like, okay, so then what's the formula for V2? Well, V2 final equals, and you just basically reverse the 1's and the 2's here. So this would be M2 minus M1, this would be 2M1, this would be M2 plus M1, but since they're both just added, you can switch them and it's okay. And then I guess that would be V2 initial. You get the idea. So this is the formula that I would memorize right here. And write it down on a piece of paper 50 times, wait a few hours, do it again just to make sure it's inside your long-term memory. And your penguin is adequately situated on the iceberg. So using this formula, we can plug in, we're looking for V1 final. That would be mass 1, so it would be 0.6 minus 0.25. 0.25. And you have to be very careful about the signs here, because this is mass 1 minus mass 2, not mass 2 minus mass 1. Mass 1 plus mass 2, that's going to be 0.85. 0.6 plus 0.25. Then we're going to multiply that by V1 initial, which is 1.2. 1.2. We'll add that to 2 times mass 2, which is 0.25. I could just write up 0.5. I did not. 0.85. And then we will multiply that by 1.8. And this is just formula based on conservation of momentum, conservation of kinetic energy. And it's totally possible you can solve it without memorizing the formula. I recommend memorizing the formula just because it's so much quicker and you're less likely to make a mistake. When you're doing a test, you're probably not going to have the time to really derive these sort of things. So we have, one thing I forgot, human force trap, negative 1.8. Not because it has a negative speed, but because that symbolizes the opposite direction. These are actually velocity vectors, not speeds. Okay, focus. So we got 0.35 over here, multiply by 1.2. Then we're going to subtract. I'm going to do quantity, 0.5, because 2 times 0.25, times 1.8. And then that negative there, I basically just moved over the negative. And then we will divide by 0.85, which should make it bigger. So we're negative 0.5647. 5647 and negative, this will be in meters per second. So we look over here, negative 0.56, negative 0.5647. They're close, so I'm going to say the answer is D. So for this second part, things to know, you have an elastic collision, therefore you started with 2 objects, you're going to end with 2 objects because they bounce off and they maintain, actually there's a conservation of kinetic energy. And you also know they have conservation of momentum, which true for all collisions, elastic or inelastic. You didn't know that this formula applies because you memorized it. It's something you should memorize. It just makes life easier. It's just for this class. It's all it's worth. Okay. Well, yeah, pretty much just for this class. In any other real life scenarios, you'd probably have time to derive it. So plug in the formula, you get a number. Make sure that you don't forget your signs because these are vectors, and so the direction is important. Your next thought might be like, well, what if it's 2 dimensions? Well, then you just break it down into your x dimension and your y dimension, and you do both of them independently. And when you get your final x and y velocities, you then combine them vectorially, i.e. through the Pythagorean theorem. So that's how you do these types of elastic collisions with conservation of kinetic energy. Hope that helped. See you next time.